Natural light comes from two sources, the sun and the sky. In these two diagrams, the length of the arrows represents the luminance distribution across the sky. A clear sky offers two natural light sources, the sun component providing direct sunlight, which is strong and dynamic, and the sky component providing diffuse skylight, which is weaker but stable. Only the sky component is present under an overcast sky. Without the sun, the luminance distribution across the sky is fairly uniform and stable, although the luminance at the zenith is approximately 3 times that at the horizon. Daylight can come from a mix of sources: direct sunlight, diffuse skylight, and reflected light from the ground and surrounding structures. Under a clear day, a building facade, for example south-facing, may receive both direct sunlight from the sun and diffuse skylight from the sky. Under an overcast sky, the building only receives diffuse skylight from the sky. The brightness of the direct sunlight varies by season, time of the day, location, and sky conditions. The intensity of the direct sunlight can be very high, exceeding 100,000 lux, or low when covered by clouds. The direction is also constantly changing. Although direct sunlight is sometimes perceived as being cheerful and exciting, a thoughtful daylighting design is required to manage sunlight, which can be unpredictable, volatile, and distracting, especially in classroom and office buildings. Diffuse skylight from either clear sky or overcast sky, on the other hand, is soft, uniform, and stable. Daylight can also come from the ground, trees, and surrounding buildings that reflect sunlight and skylight. When a new building is proposed, it is critical to ensure that the sky exposure of the proposed building is not being blocked by existing buildings, or vice versa. There are some useful rules of thumb to assess solar access among a group of buildings. For example, if the ratio of D to H in this diagram is equal or greater than 2 to 1, the windows at the lowest level of the proposed building will have reasonably good daylight access. Or if the obstruction angle theta is less than or equal to 25 degrees, the windows at the lowest level of the proposed building will have reasonably good daylight access. These rules of thumb are meant to provide simple and approximate guidelines. For any in-depth assessment tasks, physical or computer simulations may be required. As discussed previously, south-facing facades can be easily shaded with overhangs, light shelves, or louvers. North-facing facades usually receive little or no glare, although it does not provide a significant amount of solar heat for the purpose of passive heating. Northern skylight can be the best source for daylighting because it is almost always diffuse, uniform, and soft. It can be very challenging to achieve consistent daylight and glare control for east and west-facing windows. The low, almost horizontal summer sunlight makes it difficult to control. The solar gain, especially emitted in late afternoons through west-facing windows, significantly increases the cooling loads in summer months. Therefore, from the shading, passive design, and daylighting points of view, buildings that are longer on their east-west axis and having windows on south-north elevations are more desirable for energy efficiency, solar control, daylight harvesting, and visual comfort. In commercial buildings with a typical ceiling height such as 10 feet, daylight can provide a full daylight zone in the first 15 feet from the window. The next 15 feet in may or may not have decent daylight depending on orientation and sky condition. This is the partial daylight zone. The space further in receives no meaningful daylight. Large square-shaped buildings with a thick floor plate are efficient in heating and cooling because they tend to have a smaller ratio between skin and volume. However, long and narrow footprints are better than thick ones in delivering natural light to spaces, because daylight can only penetrate a certain distance. In the first example, the core has little daylight access. With the same program, if the building is shaped as a narrower bar with a 60-foot depth, all floor space can be daylit or partially daylit. With bilateral lighting, 60 feet is a maximum depth for a floor plate to be reasonably well daylit, assuming a 10-foot ceiling height. If the thickness of the floor plate is further reduced to 30 feet, such as a U-shaped floor plan, all floor spaces are in full daylit zone. However, the building is much longer and the skin to volume ratio is significantly higher, indicating a larger heat transfer rate through the envelope. Therefore, there should be a balance between compactness and daylight penetration. The range of 40 to 60 foot depth is considered as a reasonable trade-off by many designers. Although open floor plans with low partitions may not be the most desirable solution for the sake of privacy, they are the best arrangement from the daylighting point of view. The open floor layout can be modified by adding a row of private offices at the core of the floor plate for the people who need privacy. These offices can be furnished with transparent or translucent partitions facing the window walls, which allows daylight to enter. Most of the floor plan can still be furnished with open stations by the window walls. Private offices can also be located along one of the window walls to allow users in those offices to have both daylight and view. The rest of the space can be open with daylight and view through the other window wall. The most problematic design for the purpose of daylighting is a layout with the private offices on both window walls, completely blocking natural light and view from the people in the inner zones of the building. Using high reflectance values for interior surfaces, such as ceiling tiles, walls, and carpet, can have a double-digit saving on electric lighting energy usage. The ceiling is the most important surface in a space for daylighting in terms of its height and reflectance. Recommended reflectance values are 80% or higher for ceilings, at least 50 to 70% for walls, and 20 to 40% for floors. In general, the lighter the better. High ceilings can significantly improve daylight penetration from windows. A high ceiling will also allow windows to be placed high, which sends daylight deeper into the space. However, raising the ceiling height can mean raising the floor-to-floor height, which would greatly increase construction costs. Thoughtful design solutions that involve systems integration approaches are required to elevate the ceiling height without raising the floor-to-floor height, such as the design presented in the second example. The efficiency of light sources is measured by luminous efficacy, which is the luminous flux in lumens a light source generates divided by its total energy input in watt. This value represents how well a light source converts energy to visible light. In general, the efficacy of daylight is around 105 lumen per watt, higher than many conventional electric lights. This means to generate the same amount of light, daylighting produces less heat than these electric lights. This can lead to the reduction of cooling energy usage in summer cooling seasons. LED lights can have an efficacy as high as 170 lumen per watt, with the prospect of reaching 200 lumen per watt or higher. Building occupants are often concerned with how much light is delivered to work surfaces to accomplish their tasks. The most widely adopted set of standards for illuminance levels is provided by the IESNA, Illuminating Engineering Society of North America. This table shows the recommended illuminance levels by IESNA for common spaces. Another goal is to achieve a relatively good uniformity at the task surface in workspaces. In a highly ununiform lighting environment, occupants' eyes must adapt when going from a very bright spot to a very dim one, or vice versa. Light uniformity can be defined by uniformity index, the ratio of the minimum light level to the area-weighted average light level in a space. In an office with a uniformity index of 0.6 or higher, people will not notice the difference in the light level change. Glare is excessive contrast or luminance coming from the wrong direction. Direct glare is caused by excessive sunlight or a shield light fixture misdirected towards the eyes, such as the late afternoon sun through a west-facing window. A general rule of thumb is that the luminance of a light source should not exceed 1000 candela per meter square in the field of view. Reflected glare is excessive uncontrolled luminance reflected on the task in the field of view. This includes the reflected luminance from interior surfaces or from lights. With computers being used widely in work environment, the luminance of artificial lights should be maximum 1000 candela per meter square across the ceiling. Reflected glare on paper tasks is mostly experienced when lights are directly above the task. Most of the methods for sizing the window assume that if the window size works for overcast or cloudy days, they will be big enough for sunny days. The advantage of this approach is that it is simple. However, in sunny climates, they tend to oversize the windows. One of these simplified methods is the 1.5H rule. If the window head height is H, daylight can provide a full daylight zone in the first 1.5H of the space. The next 1.5H is partial daylight zone, which may or may not have decent daylight depending on orientation and sky condition. The space beyond will not receive any significant daylight contribution. Again, this method assumes the diffused light from the sky as the only light source. When direct sunlight is present, however, it tends to create a hot spot in the area close to the window, making the luminance there extremely high. Then light level drops immediately beyond this point, creating a very uneven distribution in both illuminance and luminance across the space. If the hot spot falls on a work plane, it will keep occupants from performing their tasks. Then someone will stand up and close the shade, which cuts off the view and source of daylight completely. The shades can remain closed even after the sun moves out of the view. One strategy to take advantage of the direct sunlight and maintain comfort and view is to redirect sunlight from a primary surface, such as a light shelf, to a secondary surface, the ceiling, which in turn illuminates the work surfaces. A light shelf is an interior horizontal reflecting surface mounted in the middle of the window, flush with the exterior overhang. It divides the glazing into a lower view glazing, primarily for view, and an upper daylight glazing for illumination. The outdoor overhang and indoor roller shades work together to protect the view glazing. When sunbeams are in lower angles, they can be reflected farther into the space due to their low incident angles on the light shelf. A certain amount of low sunbeams will also be emitted through the view glazing, which can be shaded by roller shades. In this case, spaces in the center zones of the floor can still have access to daylight and view through the upper glazing. When sunbeams are higher, there is no need to deploy the roller shades. In this case, people at the center can have daylight and view from both glazing areas. As another light reflecting strategy, light louvers represent a group of technologies that involve many light reflecting elements arrayed vertically, like blinds. They can be installed as a daylight glazing or placed just behind it. Light louvers are designed to emit daylight incident from a variety of directions and spread it over a substantial area of the ceiling, which then reflects the light downward to illuminate the occupied space. The advantage of the louver systems over a light shelf is that they eliminate the large light shelf surface. Upward-facing skylights are more efficient than systems involving vertical glazing, such as sawtooth or monitor, because the sky exposure of skylights is usually 100%. However, clear skylights can have negative impact on energy bills and visual comfort. They can add cooling loads in the summer and create glare due to direct sunbeam penetration. Baffles or translucent glass can be used to scatter the direct sunlight and deliver diffuse light into the space. A rule of thumb for sizing and placing standard square skylights is that the ratio of the glazing area to floor area is approximately 10%. This is assuming the space is under a diffuse sky. A sawtooth roof with vertical glazing, if designed properly, can provide uniform illumination across the space. There are rules of thumb to size the glazing area based on floor area. One of them suggests that the ratio of the glazing area to floor area be around 20%. No shading is typically required for north-facing sawtooth apertures because direct sunlight is usually not present. An overhang should be provided for south-facing glazing to protect it from the summer sun. In the winter, when sun angles are lower, additional shading such as baffles may be needed to block sunlight from entering the room to minimize glare. Roof monitors are top lighting devices involving vertical fenestration similar to the sawtooth, except that the raised roof is flat and glazing is installed on both sides. The method of sizing the glazing area for monitor apertures is similar to that for sawtooth. The 20% rule also applies. No overhang or other shading devices are needed for the north glazing of the monitors, but overhangs are recommended for the apertures facing south to protect them from the summer sun. To shade the lower winter sun angles, additional shading such as baffles may be needed to block direct sunlight from entering the room.